Welcome to solverfy.
Okay, in this problem we have sodium at 500 Kelvin, and we're asked to find the ratio in the occupancy of two different states, 3/2 and 1/2. These energy levels are shown in this figure, which is attached. So we have 2p3/2 right here. This is the first excited state, the lowest possible excited state. And here we have a similar case for 2p1/2. And we have the wavelength of photons that would be emitted or absorbed to go from the ground state to each of these excited states, given by these lines, 589 nanometers and 589.6 nanometers. So the equation we're going to need to use is the Boltzmann equation, which will relate the occupancy of two states. For this case, I'm simply writing it as n2/n1, and it's this decaying exponential, which depends on temperature and the difference in energy levels. So we'll be needing to use the Boltzmann constant K and the Planck constant H. Okay, so let's jump into it. So using the equation E equals hc over lambda for a photon, relating the energy of the photon to its wavelength, we can quickly find what these energies are from the wavelengths in the figure for the two excited states. We'll do it for one of them. So this is for the 3/2 energy level. So we have for our lambda, recall about 5.89 e to the -7 meters. And the Planck constant, we can use the Planck constant and C. So plugging this in, we end up with a result of 3.379 times 10 to the -19 joules. Okay, so this is the energy to transition to this energy level. We can do the same thing for the 1p1/2. I should just indicate that this is the lambda for p1/2 or 3/2. Doing the same thing for 1/2. We use a lambda of 5.896, so very, very similar. And same H and C constants. We end up with a result that's very similar, but not quite the same as the previous result, 3.371. So now that we have these two energy differences, we can go to the Boltzmann equation and express this difference in occupancy as a ratio, n2/n1. So we'd have E to the negative first energy minus second energy. So 3.379 E -19 minus the result for 1, 2, 371 E -19. And we need to divide this all by KT, where K is the Boltzmann. Ooh, let's do a better job with that line. So we need to use the Boltzmann constant and the temperature. 1.38 times 10 to the -22, or 23 rather, joules per Kelvin, multiplied by 500 Kelvin, which is the temperature this system is at. So plugging this all in, we will end up with 0.944. And that's it. So slightly difference, but roughly the same. Thank you very much.